Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. So the next applications of mass conservation equations that we looked at is related to an unsteady flow case. So here we have a tank, and at the bottom of the tank there is a hole. So a 3 centimeter jet of water issues from a 60 centimeter diameter tank, as shown in this diagram here. Assume that the velocity in the jet is equal to root 2gh meter per second. So the velocity of this jet exiting from this hole at the bottom here is equal to root 2gh meter per second. So we are asked to calculate how long will it take for the water surface in the tank to drop from h0 is equal to 3 meter initially to hf is equal to 30 centimeter. So let's consider the tank here. So the tank has a diameter big D is equal to 60 centimeter. And let's call the cross-sectional area of the tank is 80. And then let's call the diameter here is equal to small d. And the jet exit this hole at the bottom, and the velocity at outlet is equal to root 2gh. And let's say the area here of the hole is equal to a naught. So first of all, let's determine our control volume. The whole of this is actually our control volume. So first of all, so we apply the mass conservation equations to the control volume. So the general mass conservation equations dmc by dt is equal to mass flow rate in minus mass flow rate out. So this case is incompressible flow. So that means the density is equal to constants. So we know that mass is equal to rho multiplied by volume, right? So our mass conservation equations now become the rate of change of volume, control volume, is equal to volume flow rate in minus volume flow rate. So now let's consider each of these terms one by one. First of all, let's consider the volume. So the volume of water in the tank will be equal to the cross-sectional area of the tank, AT, multiplied by the height. So that is equal to a tank multiplied by the. So this implies that first term, dvc by dt, that is equal to d by dt, a multiplied by h. Now what about the second term? The volume flow rate in, since we don't have any inlet, so that's equal to 0. Then the volume flow rate out, we only have one exit through the hole at the bottom here. So that's equal to volume flow rate out here, and that is equal to V out, A out, and given that V out is root 2gh, so that's A naught root 2gh. So now we can substitute into the equations, substituting into the mass conservation equation, which is this equation here. So this will give us d by dt ah, and this must be equal to minus a naught root 2gh dt, and that is equal to minus a naught root 2gh to the half, right? So now I can rearrange this a little bit. So I have minus 80 over a naught root 2g integral of 1 over h to the half dh must be equal to dt. So bring this to this side and then bring this h to this bottom here. Bring h to the half to the bottom here. So I will obtain these equations. So we have to integrate from H initial to H final, from t equal to 0 to t equal to big T. So we need to determine what is the value of T. We consider the tank. H initial is equal to 3 meters. And then after that, the height of the water will reduce such that H final is equal to 30 cm or 0.3 meter. So that means that we need to integrate 80 over A naught root 2G from H equal to 3 to H equal to 0.3 1 over H to the half TH, and that will be equal to dt from 0 to t. So if we do this integration, I bring this to the left, so I have, so this will give us 0t, and that is minus 80 over a naught root 2g to h to the half, because if we integrate this, we'll have h to the half multiplied by 2, so from 3 to 0.3. So this gives us t equal to area of the tank 0.6 squared over 4 divided by area of the hole by 0.03 squared over 4 divided by root 2 9.81 multiplied by 0.3 minus 3.5. So this gives the time taken is equal to 212.95 seconds. So that means that it will take 212 seconds for the water level to fall from 3 meter to 30 centimeter.